This is the 21st video in a series on introductory proofwriting. And today we're going to look at basic proofs involving sequences and series. So let's start with what it means for a sequence to converge. And so maybe before that even, we should just recall that a sequence is a list of numbers. So like 1, 3, 5, 7, 9, that's a sequence. And that's the list of all odd numbers. So that would be the sequence of all odd natural numbers. But we generally write sequences with indices. So like A1, A2, A3, A4, A5, so on and so forth. And then we package all that up into the following notation. So a sequence, which we'll write curly braces A sub n, converges to L, and in that case we will write the limit as n goes to infinity of A sub n equals L if for every epsilon bigger than 0 there is a natural number n such that if little n is larger than capital N, then the absolute value of A sub n minus L is less than epsilon. So what this means is that we can always make the terms of our sequence very, very close to the limit of the sequence if we look far enough into the sequence. So here's a picture of that happening. So let's say here's our limit L. I've put my epsilon bound around L, and I've put my n here. And notice my sequence is in this magenta chalk, and once we get past this capital N, we're always within our epsilon band. And the idea is that you can squeeze this epsilon band closer to L, and that will push this capital N further out. But you can always find a capital N where after that point, you're always within epsilon of your limit. Okay, so now that we've looked at that precise definition, let's show that a few sequences have certain limits using this precise definition. So let's maybe first consider the following sequence, which is of the form 3n plus 1 over 2n plus 4. And then I'm going to introduce some more notation. Sometimes you write here that n goes from 0 or maybe 1 to infinity. There could be a different starting point though. Okay, so let's write the first couple of terms of this. So if we plug in n equals 1, we will have 3 plus 1, which is 4 in the numerator, and then in the denominator we'll have 2 plus 4, which is 6. So we have 4 over 6. So that can pretty clearly be simplified, but we won't simplify it. If we plug in n equals 2, we will have 7 over, let's see, plugging 2 in here, we'll have 8. Good. Then if we plug in n equals 3, we'll have 9 plus 1, which is 10, over 6 plus 4, which is also 10. Okay, then you can see this goes on and on and on. Great. And now probably from calculus, you know that the limit here should be the ratio of the leading coefficients. So it should be 3 over 2, and that's what we'll show. So let's maybe do that in the form of a claim. So let's make our claim, which is the limit as n goes to infinity of 3n plus 1 over 2n plus 4 is in fact equal to 3 over 2. And if you recall how we proved certain limits had values in our previous video when we talked about functions, there was a bit of scratch work to do to get ourselves set up. And in fact, in this case, there's also a bit of scratch work to do in order to get ourselves set up. This is kind of like solving the problem in reverse and then rewriting it in the forward direction. Okay, so let's start with where we want to end up, which is 3n plus 1 over 2n plus 4 minus 3 halves is less than epsilon. Of course, that's within an absolute value. So that's the nth term of our sequence minus the would-be limit of our sequence. But now we probably want to simplify what's going on in the absolute value. We can do that by finding a common denominator. The denominator on this left-hand term is already even, so we only have to build up the denominator on the right-hand term. And we'll do that by multiplying by n plus 2 over n plus 2. That gives us 3n plus 1 over 2n plus 4, just bringing that down, minus 3n plus 6 over 2n plus 4, like that. We want that to be less than epsilon. But let's see, that's going to simplify to 5 over 2n plus 4 is less than epsilon. But now we can start doing a little bit of simplification and notice that 5 over 2n plus 4 is itself less than 5 over 2 times 1 over n. And that's just from dropping the plus 4 in the denominator, which makes our whole thing larger. So if we can pin that smaller than epsilon, then we're good to go. But notice that means 1 over n is less than 2 over 5 epsilon. Maybe 2 epsilon over 5, which is the same thing as saying n is bigger than 5 over 2 epsilon. And this 5 over 2 epsilon is what we will take for our capital N. Okay, so now we're set up to write our proof in the proper order. Okay, so let's say we're given an epsilon bigger than 0. Let's take our capital N, which is a natural number, so that capital N is larger than 5 over 2 times epsilon. We can't really take it to be equal to 5 over 2 times epsilon because this may not be a natural number. But by the Archimedean principle, we know that for any real number, we can find a natural number larger than that real number. Okay, and now looking over here at the definition, we need to prove this conditional. So if little n is bigger than capital N, then a sub n minus L is less than epsilon. This is our a sub n minus L less than epsilon in our case. Okay, so let's get to it. So let's suppose that little n is bigger than capital N and then make the following calculation. So we'll have the absolute value of 3n plus 1 over 2n plus 4 minus 3 over 2, which is equal to the absolute value of 5 over 2n plus 4 by the calculation that we did over there. But that is less than 5 halves times 1 over n. We can drop the absolute value because everything in there is positive at this point. And the inequality comes from the fact that we made the denominator smaller. But now since lowercase n is bigger than uppercase n, we know this whole thing is less than 5 over 2 times 1 over capital N. But since capital N is larger than 5 over 2 epsilon, it means 1 over capital N is smaller than 2 over 5 epsilon. So we have this is less than 5 over 2 times 2 over 5 epsilon. But now those two cancel, giving us epsilon. So let's see. Have we done it? Yes. We said if n is larger than this capital N, then our a sub n minus L is less than epsilon. So that means we've proven this claim. Okay, let's do another. For our next example, we'll show that the limit as n goes to infinity of n over n squared plus 1 is equal to 0. And we'll do this with our scratch calculation and then final draft approach. Okay, so for our scratch calculation, we'll look at our goal, which is to show the absolute value of n over n squared plus 1 is less than epsilon. But notice all of the terms here are bigger than 0, so this is equivalent to saying n over n squared plus 1 is less than epsilon. Notice it looks like I'm not subtracting the limit, but the limit is 0, so the minus L is just minus 0 in this case. Okay, now where can we go from here? Well, we'll do a similar trick as we did in the last board, and that is we'll drop this plus 1, creating something larger. So in other words, we'll look at n over n squared, which is larger than n over n squared plus 1. So we made the denominator smaller, which made the entire thing larger. But notice that is 1 over n, and if we can get this less than epsilon, then our thing is also less than epsilon. But in fact, we can make that less than epsilon fairly easily just by picking n to be bigger than 1 over epsilon. So that'll be our choice for capital N, or our choice that we want our capital N to be larger than. Okay, so now I think we're ready to write down this proof. So let's say we're given some epsilon bigger than 0. Let's take our natural number capital N so that capital N is larger than 1 over epsilon. But now that means that 1 over capital N is less than epsilon. Okay, now we're ready to finish this thing off. So let's suppose that little n is bigger than capital N and observe that the absolute value of n over n squared plus 1 is equal to n over n squared plus 1 because we don't really need the absolute value, but that is less than n over n squared because we've made the denominator smaller, thus making the whole thing larger. But that's equal to 1 over n, but that is less than 1 over capital N, given that little n is bigger than capital N. But that is in turn less than epsilon by this observation that we made up here, which was born out of the way that we chose our capital N in the first place. So let's see, we started with an n larger than this capital N, and we ended with our term minus its limit is less than epsilon, which is exactly what we needed to prove that this limit was 0. Okay, let's look at a different type of limit. Now we'll look at a different type of a limit where the limit maybe does not converge, but it diverges to infinity. So let's say we're given a sequence a sub n. We say that the limit as n goes to infinity of a sub n equals infinity if for every real number capital M, there is a capital N, which is a natural number, such that if little n is bigger than n, then a sub n is bigger than m. So instead of trying to get the terms of the sequence close to some limiting value, we want to drive the terms of the sequence as large as we can. So you think about this capital M as a very large number, and we can always achieve a tail of this sequence, which is always over that large number. Okay, so let's look at a couple of examples. So let's maybe start with a fairly simple example, which is the sequence 2 to the n, so powers of 2. So let's notice that this is 2, 4, 8, 16, 32, so on and so forth. So that pretty clearly diverges to infinity, or it has a limit which is infinity. But let's maybe check that. So we'll do this with a scratch work and then forward direction proof just like before. So let's lay out our scratch work. So what we want is for 2 to the little n to be bigger than some real number m. So I think one way to do this would to be as follows. Notice if we take capital N bigger than m, then 2 to the n is always bigger than n. So if you put something in an exponent, you'll always get something larger than what's in the base. But that is bigger than m. So maybe something like this works, but this is really just like some scratch work, right? And that really kind of tells us the need for the following lemma. So the lemma would be something like this. So maybe for all n, which are natural numbers, we have 2 to the n is larger than n. I think something like this might help us out. Okay, so now let's go over here and prove that lemma using induction, and then we can apply the proof of that lemma or apply the result of that lemma to our final goal. Okay, so let's say lemma for all natural numbers n, we have 2 to the n is larger than n. Okay, so like I said, we're gonna do this by induction, which means we'll first need our base case. So our base case is the n equals 1 case, that's the smallest natural number, and it holds pretty clearly in this case. So we have 2 to the 1 is equal to 2, which is bigger than 1. So we're good to go there. And now let's make an induction hypothesis. So let's suppose for some k bigger than or equal to 1, we have 2 to the k is bigger than k. So something like that. And then let's consider the next case. So we'll consider the 2 to the k plus 1 case. Okay, but now notice that 2 to the k plus 1 is equal to 2 times 2 to the k. But that is larger than 2 times k by the induction hypothesis. But 2 times k is equal to k plus k, just by the definition of multiplication. But then, since k is bigger than or equal to 1, we know this is bigger than or equal to k plus 1, just replacing one of those k's with 1. But now we have proved our induction step. Notice we have 2 to the k plus 1 is larger than k plus 1. So that finishes this proof. And now we're ready to prove that this sequence in fact diverges to infinity. But let's maybe do that in the place of this proof right here. Now that we've got our lemma, we're ready to prove our claim. So let's say we are given some real number, which we assume to be quite large, but it's not written that it's quite large. So we've got a real number m. Now let's take a natural number, which we'll call n, such that that natural number is bigger than our real number. So this is always possible by the Archimedean principle. And now suppose that our lowercase n is bigger than our uppercase n, and notice that 2 to the n is larger than n by the Archimedean principle, but that's larger than our capital N by this assumption right here, but that's larger than our capital M by our setup here. So in the end, we've pushed 2 to the n larger than m, which, if you look carefully at the definition over here, is exactly what we need to do to show this limit is infinity. Okay, let's do a related problem. Next up, we'll look at the sequence 2 to the n over n. And probably from a calculus class, you know that this should also diverge to infinity. And that's because the denominator is acting like a polynomial, whereas the numerator is acting like an exponential function. And exponential functions always grow faster, or they always win. But how would we show this? I think maybe to show this super carefully using the tools that we have, we could start with the following lemma, which says for all n bigger than or equal to 2, 2 to the n is bigger than or equal to n squared. But if 2 to the n is bigger than or equal to n squared, then that'll nicely interact with the denominator that we have here. So that's a sketch of where we would go with this. Okay, now let's prove this with induction. Notice our base case will be the first case satisfied, which is n equals 2 here. So if we plug in n equals 2, we get 2 to the 2, which is equal to 2 to the 2. Great. So that's really all there is to that. Now let's make an induction hypothesis and then prove our induction step. So let's suppose for some k bigger than or equal to 2, we have 2 to the k is bigger than or equal to k squared. And then we'll consider the next case. So, and consider, like I said, the next case, which is 2 to the k plus 1. So let's notice that that is equal to 2 times 2 to the k. But now we can apply our induction hypothesis to take care of this 2 to the k. So this is bigger than or equal to 2 times k squared. Okay. But then we can rewrite this as k squared plus k squared. And then from here, you might need another little bit of an inequality, which I'll leave as a homework lemma. And that says that this is bigger than or equal to k squared plus 2k plus 1. And so let's just sketch out what's needed for that. And that is to show that k squared is bigger than or equal to 2k plus 1. Which is definitely true after a point. Okay, so that would maybe be something to add into this to like clear up all of the gaps. But now k squared plus 2k plus 1 is equal to k plus 1 squared. So we in fact have 2 to the k plus 1 is bigger than or equal to k plus 1 squared as needed to finish this induction proof. Okay, so now let's prove that this sequence in fact diverges infinitely. Now we're ready to finish this example off. So let's say we are given some m, which is a real number. Now let's take some natural number n such that capital N is larger than this real number m. So again, always possible by the Archimedean principle. And now we'll suppose that lowercase n is bigger than capital N, and observe that this essentially takes us home. So we have 2 to the little n over n is bigger than or equal to little n squared over little n by our lemma, which is equal to little n, which is bigger than capital N, which is bigger than capital M, as needed. So that's what finishes this proof off. Okay, now let's look a bit at series. Now we're gonna look a very little bit at series. So let's recall that the series, which can be written as the sum as n goes from 1 to infinity of a sub n, converges to S if the sequence of partial sums also converges to S. Let's recall the sequence of partial sums, which we'll denote by S sub n, is equal to a1 plus a2 all the way up to an. So I think it's aptly named sequence of partial sums. Let's also recall that if the limit of the sequence of partial sums either does not exist or is plus or minus infinity, then we say that this series diverges. Okay, so let's look at a couple of examples, starting with the sum of 1 over 2 to the n. Okay, so let's look at a couple of cases of the sequence of partial sums to get an idea for what's going on here. So notice that S sub 1 is simply 1/2. That's the first term. S2 is equal to 1/2 plus 1/4, which is equal to 3/4. S3 is equal to 1/2 plus 1/4 plus 1/8, but that's 3/4 plus 1/8, but that's 6/8 plus 1/8, which is 7 over 8. Then maybe S4 you can calculate to be 15 over 16. So notice the denominators are always powers of 2, and the numerators are 1 less than those powers of 2. So that maybe brings us to the following claim, which would be S sub n, which is equal to 1/2 plus 1/4 plus all the way up to 1 over 2 to the n is equal to 2 to the n minus 1 over 2 to the n. Okay, and now let's prove this by induction. But if we can prove this by induction, then we're probably done, and that's because we can rewrite this as 1 minus 1 over 2 to the n, which has a limit which is equal to 1, which maybe we won't show, but you would show that exactly the same as we showed these other limits were equal to 1. So anyway, let's, like I said, prove this by induction. Notice the base case is done by our preparatory calculation. So let's make an induction hypothesis and prove the induction step. So let's suppose for k bigger than or equal to 1, we have S sub k is equal to 1 minus 1 over 2 to the k, as we calculated up here and surmised. Okay, now next, let's consider the next partial sum, which is S sub k plus 1. But notice that's exactly equal to S sub k plus 1 over 2 to the k plus 1. And that's because in general, a sub k plus 1 is all that you need to add to the kth partial sum to get to the k plus first partial sum. Now we'll apply our induction hypothesis to get 1 minus 1 over 2 to the k plus 1 over 2 to the k plus 1. Okay, but now we can simplify this pretty easily by giving ourselves a common denominator. We can add 1 here if we multiply by 2 here, and then if we subtract those, we get 1 minus 1 over 2 to the k plus 1, just as needed. And that proves the closed form of the sequence of partial sums in order to prove that this is in fact equal to 1, because the limit of the partial sums is equal to 1. You would have to prove that carefully with the epsilon n definition of the limit of the sequence like we've been doing, but I'll maybe leave that as a little bit of a homework exercise. It follows very similarly to the other examples we did. Okay, let's do another. For our next example, we'll look at the sum as n goes from 1 to infinity of 1 over n squared plus n. And here we're going to take motivation from calculus, where we did partial fraction decomposition. And let's take this 1 over n squared plus n, and note that we can rewrite it 1 over n minus 1 over n plus 1. So if we give those things a common denominator, we'll see that that works exactly. And now let's write our nth partial sum. So notice s sub n will be the first term, so that'll be 1 minus 1/2 plus the second term, which is 1/2 minus 1/3, plus the third term, which is 1/3 minus 1/4, all the way up to the nth term, which by our decomposition is that thing over there. So this is 1 over n minus 1 over n plus 1. But notice there's a lot of cancellation here. We get this half cancels this half, this third cancels this third, this quarter will cancel this quarter, all the way down to this 1 over n will be canceled by something before it, leaving us with 1 minus 1 over n plus 1. But perhaps we would really want to prove this carefully with induction. So let's see how we would lay that out. So let's make our claim that s sub n is 1 minus 1 over n plus 1 in this case. So notice that our base case will be the n equals 1 case here, which will be just 1 over 2, which is equal to 1 minus 1/2. And now let's make an induction hypothesis. So let's suppose for some k bigger than or equal to 1, we have s sub k is equal to 1 minus 1 over k plus 1, and let's consider the next term. So s sub k plus 1 will be s sub k plus the k plus first term, but we'll take this format for the k plus first term. So this will be 1 over k plus 1 minus 1 over k plus 2. But now we can use our induction hypothesis to rewrite this s sub k as 1 minus 1 over k plus 1, and we'll see that these 1 over k plus 1s cancel, and we're left with exactly what we need, which is 1 minus 1 over k plus 2. So that establishes this closed form here. But now all we have to do is take the limit of this sequence of partial sums. Again, proving that carefully using our epsilon n method, we'll see that this goes to the number 1. So that means the value of this series is 1. Okay, let's look at one more series. Now we're going to look at a famous series known as the harmonic series. So that's the sum of terms 1 over n, the sum of reciprocals of natural numbers. So in other words, this is like 1 plus half plus third plus quarter plus ... And maybe surprisingly, we'll show that this diverges, which you probably saw in a second semester calculus class already. Okay, so let's see how to do that. Instead of taking the nth partial sum, we'll take the 2 to the nth power partial sum. So let's see, s sub, like I said, 2 to the n. So that'll be 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8. And like I said, ending way out here at 1 over 2 to the n. Okay, nice. And now we're gonna make some replacements. So let's maybe group 1/3 and 1/4 and we'll replace 1/3 with 1/4. We'll group a 5th through an 8th and we'll replace a 5th, a 6th, and a 7th with an 8th. And then we'll continue to do that. But making those replacements means that we have something smaller, because a 1/4 is smaller than a 1/3 and an 1/8 is smaller than a 1/5, and so on and so forth. So that means our starting thing is greater than 1 plus 1/2 plus a 1/4 plus a 1/4 is a 1/2. An 1/8 plus an 1/8 plus an 1/8 plus an 1/8 is also a 1/2. And you'll see that we have just a bunch of strings of 1/2. But how many strings of 1/2 do we have? Well, we have exactly n copies of 1/2, and that's because we went out here to 2 to the nth power. So that's pretty clear here because this is 2 to the 3rd power, and after 1 over 8, so going out that far, we have 3 copies of 1/2. Okay, so notice that we can put all these together and we'll get 1 plus n over 2. But now that clearly goes to infinity as n goes to infinity, which again, you can check with an mn argument like we did before. But the important thing here is that we have shown that this harmonic series is in fact divergent. So we have a divergent series. Okay, so now let's prove a general result before I leave you with some warm-ups. Now we're gonna prove a result whose contrapositive is known in a calculus class as the test for divergence. So in particular, we'll show that if the sum as n goes from 1 to infinity of a sub n converges, then the limit of the terms equals 0. Let's recall the contrapositive says that if the limit of the terms is not 0, then our series diverges. Okay, so let's get going with the proof. So let's suppose that the sum as n goes from 1 to infinity of a sub n has a value of s. And then let's also set s sub n to be the nth partial sum. So a1 plus a2 all the way up to a sub n. So we know that s sub n converges to s. So let's use that via the definition of convergence for a sequence. So let's say we're given an epsilon bigger than 0. Let's take our capital N, which is a natural number, such that if little n is bigger than capital N, then the absolute value of s sub n minus s is less than epsilon over 2. Now we'll choose epsilon over 2 for a reason which will come up. And we're allowed to do all of this because we know something about the convergence of that sequence of partial sums. Okay, so now let's observe that if little n is bigger than capital N minus 1, so that's our new capital N in this case, it's just capital N minus 1, or capital N plus 1, I should say. And that's because that means n minus 1 is larger than n, just for what it's worth. We have the following result. So let's notice the absolute value of a sub n is the same thing as the absolute value of s sub n minus s sub n minus 1, the nth partial sum minus the n minus first partial sum. Notice that's just taking all of these terms and subtracting off all but one of them. But now we'll add a version of 0 in here. This is equal to the absolute value of s sub n minus s plus s minus s sub n minus 1. Like I said, just adding a version of 0 in there. But now we can apply the triangle inequality to see that this is less than or equal to the absolute value of s sub n minus s plus the absolute value of s sub n minus 1 minus s. But since n minus 1 is larger than n, and that means that n is also larger than n, we know that each of these is strictly less than epsilon over 2 by our setup right here. But that's equal to epsilon. But that means we have our a sub n term is less than epsilon, which is exactly what we need for its limit to be 0. Okay, so now I've got some warm-ups for you. Now I've got 3 warm-up problems for you. So the first is to show using the epsilon n definition of a limit of a sequence that the limit as n goes to infinity of n minus 3 over 2n plus 5 is 1/2. Next, show via partial sums and stuff like that, that the sum as n goes from 1 to infinity of 1 over 3 to the n is equal to 1/2. So at the end of this, you'll need an epsilon n proof that the limit of the sequence of partial sums is what you want it to be. And then finally, a little bit more general of a proof, which you can adapt something from what we did in a previous video, and that is show that the limit, if the limit as n goes to infinity of a sub n is L, and the limit as n goes to infinity of b sub n is m, then the limit of the sequence built out of the sum of the terms is L plus m. And that's a good place to stop.